I'll prove this performance guarantee for you on the next slide, but let me first make a couple of comments. So first of all, the analysis of this algorithm stated in the theorem is tight. The 50% cannot be improved without making additional assumptions about the input. Indeed, here's an example, which is itself is even a bipartite graph, so it's a tractable special case of maximum cut. But even on bipartite graphs, the local search heuristic might return to you a cut which has merely 50% of the edges of a globally optimal maximum cut. The example is drawn here in green. There's just 4 vertices and 4 edges. As I said, it is a bipartite graph, so the best cut is just to put U and W in one group and V and X in the other group. That cuts all 4 of the edges. On the other hand, one possible output of the local search algorithm is the cut where U and V are in one of the groups A and W and X are the other group B. So this cut has only 2 crossing edges, only 50% of the maximum possible, yet it is locally optimal. If you take any of the 4 vertices and you switch it to the other group, you get a cut with 3 vertices on one side and then the other vertex by itself. Since every vertex in this graph has degree 2, all of those cuts are also only going to have 2 crossing edges. The second cautionary point that I need to tell you is that you maybe shouldn't be super impressed with a performance guarantee of 50% for the maximum cut problem. Indeed, even if I just took a uniform at random cut, by which I mean for each of the n vertices, I flip independently a fair coin. If the coin comes up heads, I put that vertex in A. If the coin comes up tails, I put that vertex in B. The expected number of edges that cross a random cut chosen in this way is already 50% of the edges of the graph. Just for kicks, let me sketch a quick proof of this fact. Some of you may remember from part 1, I introduced a decomposition principle for analyzing the expected value of complicated random variables. You have a complicated random variable that you care about. What do? You express it as the sum of indicator random variables that only take on the values 0 and 1. Then you apply linearity of expectation that reduces computing the complicated expectation to a sum of simple expectations. So it turns out that decomposition principle works beautifully to prove this fact. The complicated random variable that we care about is the number of edges that cross a random cut. The constituents that are indicator 0, 1 random variables are just whether or not a given edge crosses a random cut. That is, for an edge E of this input graph G, I'm going to define the random variable x sub E to be 1 if its 2 endpoints wind up in different groups, and 0 if its 2 endpoints wind up in the same group. So what's the expected value of one of these indicator random variables x sub E? Well, as with any indicator random variable, that's just the probability that x sub E is equal to 1, the probability that this edge E is cut by a random cut. What's the chance of that? Well, let's say the endpoints of edge E are U and V. There's 4 possibilities. U and V could both be in A, U and V could both be in B, U could be in A and V could be in B, or U could be in B and V could be in A. Each of those 4 outcomes is equally likely, probability 1/4. In the first 2 cases, this edge is not cut by the random cut. The 2 endpoints are on the same side. In the other 2 cases, it is cut. They're on different sides. So it's a 1/2 probability that this edge is cut in a random cut. Therefore, the expected value of x sub E is 1/2. And now we're good to go just by applying linearity of expectation. So precisely what do we care about? We care about the expected number of edges that cross a random cut. Well, the number of edges crossing a cut is, just by definition, the sum of the xe's over all of the edges E. Xe is just whether or not a given edge crosses the cut. So the expected value of the random variable we care about, the number of crossing edges, that's by linearity of expectation, just the sum of the expected values of these indicator random variables, the x sub E's. Each of those has value 1/2. We're summing up 1 for each of the edges. So the total of the sum is just the number of edges divided by 2 as claimed. Thanks for indulging my little digression. Again, the point of which is that just taking a random cut gives you a performance guarantee of 50% for the maximum cut problem. But in the defense of local search, which also only gets a 50% performance guarantee, it took a while, and in fact you have to work pretty hard to get a performance guarantee better than 50% with a polynomial time algorithm for the max cut problem. The most famous such algorithm is by Gomez and Williamson. That took till 1994, and it requires a tool called semi-definite programming, something that's even more powerful than linear programming. Let's now prove that local search is guaranteed to output a cut whose number of crossing edges is at least half the total number of edges in the graph. So pick your favorite locally optimal cut AB. And here by locally optimal, I just mean something that the algorithm might return. That is, a cut for which it's impossible to swap a single vertex from one side to the other and improve the value of the cut. By virtue of being locally optimal, it must be the case that, for this cut AB, and for every single vertex V, the number of edges incident to this vertex that are crossing the cut is at least as large as the number of vertices incident to this vertex that do not cross the cut. So in the previous notation, C sub V is at least as big as D sub V. If not, swapping V would give us a better cut. So we have n of these inequalities, once for each vertex V, so we can legitimately sum up those n inequalities, combining them into one. Now let's focus first on the right-hand side of this summed up inequality. So the sum over all of the vertices in the graph of the number of edges incident to that vertex that are crossing the cut. Now here's the main point. What is this sum on the right-hand side counting? It's counting each edge that crosses the cut AB exactly twice. Consider an edge, say U comma W, which is crossing the cut AB. It gets counted twice in its right-hand side. Once when V equals U, and once when V equals W. We can apply exactly the same reasoning to the left-hand side. What is this sum counting? It's counting each non-crossing edge exactly once. Consider an edge, again, say U comma X, whose both endpoints are on the same side. That's going to be counted once in this sum when V equals U, and then again when V equals X. Now we want to compare the number of crossing edges of this locally optimal cut to the total number of edges. So on the left-hand side, we're missing the crossing edges. So to complete that into all of the edges, let's just add double the number of crossing edges to both sides of this inequality. On the left-hand side, we get double of all of the edges, and now on the right-hand side, we have 4 times the number of crossing edges. Dividing both sides of this inequality by 4, we see we've proved the theorem. The number of edges that cross A comma B is indeed a full 50% or more of the total number of edges in the graph. It's interesting to discuss briefly how the conclusions we've reached for local search for max cut extend to a natural weighted version of maximum cut. So which facts about the unweighted special case extend to the weighted case and which facts do not? Well, it still makes perfect sense to take a local search approach to the weighted version of the maximum cut problem. Now, for each vertex and in a given cut, you just look at the total weight of the incident edges that are crossing the cut and the total weights of the incident edges which are not crossing the cut. And whenever the weight of the edges not crossing the cut is strictly bigger, that's an opportunity to improve the current cut by moving the vertex to the opposite side. One cool thing is that the performance guarantee that we just established of 50% for the output of local search, that carries over to the weighted case, and the proof remains essentially the same, and I'll leave it for you to check that in the privacy of your own home. Now, it's also true that in the weighted case, a random cut still gets 50% of the total weight of the graph, so perhaps this performance guarantee is nothing really to write home about. What breaks down is the running time analysis. Remember how this went for the unweighted case. We argued that there can be at most n choose 2 edges crossing any cut, and since every iteration of local search increases the number of crossing edges, it has to halt within a quadratic number of iterations, and that means it's easy to implement the algorithm in polynomial time. One way to think about what's special about the unweighted version of the maximum cut problem is that even though, as we've seen, the graph has an exponential number of different cuts, all of those exponentially many cuts only take on a polynomial number of different objective function values. The number of crossing edges is somewhere between 0 and n choose 2. By contrast, once the edges can just have any old weights, now you can have an exponential number of cuts with an exponential number of distinct objective function values, of distinct values for their total weight. That means just because you're strictly improving the total weight crossing the cut in each iteration, it does not imply that you're going to converge in a polynomial number of iterations. And in fact, it's a highly non-trivial exercise to prove that there are instances of weighted maximum cut in which local search takes an exponential number of iterations before converging.